In this video, we'll apply the second law of thermodynamics and the Clausius inequality relationships that we developed in the previous video to derive the expression for the Gibbs energy. We go back, and actually if we go back to the previous video, after we developed the basic relationships that we use with the Clausius inequality, at what point we came up with this expression here, which relates the differential of internal energy and the product Ts being less than or equal to the expression on the right. So we had this inequality that we derived in the previous video. You'll have to go back to the previous video to look at that if you've forgotten how to derive that. So if we use a relationship here with dW, and now we're not limiting work to just expansion work. We are going to include expansion work and non-expansion work in this. So that could include, for example, electrical work. Alright, so making the substitution for work in the top expression, we get this particular inequality here, which includes the non-expansion work in the expression. And then we're going to do something like we did in the previous video. We're going to add these two terms, VDP and minus VDP, and of course the two terms together are equal to 0, so we're adding 0 to the expression, but we're going to find this to be useful because we can combine the VDP term and the PDV term into one term, dPV, and then we can take that term, move it to the left side of the equation, so we get the inequality here where on the left side we have du minus dTs plus dPV being less than or equal to, on the right side, minus SDT plus dW non-PV work, non-expansion work, plus VDP. Alright, now, if we use the definition of enthalpy, we have dH is equal to du plus dPV, and if we look down here at our expression, we'll find that we actually have those terms, so we can combine those terms to give us dH, which simplifies our expression a bit. So now we have on the left side dH minus dTs, and you may already recognize that from previous discussions that this is in fact the definition of the Gibbs energy. G is defined as being equal to H minus Ts. So taking the expression above, making the new definition of G, gives us this expression here. Alright, now if we consider an isothermal and an isobaric process, the first two terms in that expression will be 0, dt will be equal to 0, dp is equal to 0. So for an isothermal isobaric process, we have the following down here at the bottom of the page, where dg is less than or equal to dw non-PV work. So this is the situation where dg is less than or equal to dw non-expansion work. If we do not have any non-expansion work, then this will be, of course, 0. We'll come up to that in a second. But this is one of the crucial things that the Gibbs energy tells us. You may remember from our previous video that the Helmholtz energy allowed us to determine the maximum amount of work we can get from the system for an isothermal process. Here we have the Gibbs energy, which will tell us the maximum amount of non-PV work we can get from a system under conditions of isothermal and isobaric process. So again, the Gibbs energy tells us the maximum non-PV work we can get from a system during an isobaric and isothermal process. And again, this would be a situation where if we wanted to know, for example, the maximum amount of electrical work we can get out of an electrochemical process, then when we calculate delta G, that will tell us the maximum amount we can get from that electrical process. And of course, if we have expansion work only, that means delta G is going to be less than or equal to 0. Now, again, the key here is that just as was the case for the Helmholtz energy, which we discussed in the previous video, the Gibbs energy derivation here is also based on the second law of thermodynamics, which includes the universe. So this entire expression here is based on delta S for the universe being greater than or equal to 0. So if we have an isothermal isobaric process where the only type of work is expansion work, then delta G being less than or equal to 0 is a requirement of the second law. We no longer have to calculate delta S for the surroundings as we did for the irreversible phase transition problem we did in a previous video to determine whether it will be spontaneous or not. In this case, we are simply calculating delta G, and if delta G is less than or equal to 0, we know it's going to be spontaneous. If it's less than 0, if it's equal to 0, of course, we have equilibrium. So that's all we need to do. We do not have to explicitly calculate delta S for the surroundings to figure this out. Delta G has embedded in it, through the second law, through the Clausius inequality, that condition associated with the surroundings. So this is the advantage of delta G for an isobaric process and delta A for an isochoric process, that if we calculate these thermodynamic parameters, we will be able to determine the spontaneity of a process without having to calculate the process or calculate delta S for the surroundings. Again, these are calculations based entirely on system variables and do not require us to calculate explicitly delta S for the surroundings. And this is the real advantage of delta G for, again, the isothermal isobaric process, and delta A for the isothermal isochoric process. Now, in our next video, we'll be looking at further applications of the fundamental equations of thermodynamics, and we'll be relating delta A and delta G to equilibrium systems.